Hey there, and welcome. Have you ever looked up at a twin-engine prop plane and just wondered what's really going on up there? With all those incredible forces? Well, today we're going to dive into a really fascinating piece of aerodynamics, one that has huge implications for pilot safety. All right, so let's set the scene. Imagine you're in the cockpit of a twin-engine plane, and boom, one of the engines just quits. The big question, the one you have to answer in a split second, is this. Does it matter which one failed, the left or the right? I mean, you think an engine is an engine, right? But the answer is way more complex than you might think.
And yeah, here's the kicker. On most propeller planes out there, it matters. It matters a lot. The failure of one of those engines is actually way more dangerous than the other. And that, my friends, is the whole mystery behind what pilots call the critical engine. Okay, so our first order of business here is to figure out who the culprit is. What exactly makes one of these engines so critical?
So the critical engine, what is it? Well, the official textbook definition says it's the engine whose failure has the most adverse effect on directional control. Okay, let's translate that. In plain English, it's the engine that when it fails makes the plane the absolute hardest to fly. It's the one that's going to give the pilot the biggest headache. And here it is, the big reveal. On almost all conventional twin-engine planes made in the US, the ones where both props spin clockwise, it's the left engine. The left one is the critical one. So the question isn't which one anymore, it's why the left one.
To get to the bottom of this, we've got to put on our detective hats. And luckily, pilots have this awesome little acronym to help us remember the four main reasons this all happens.
That acronym is PAST. PAST. It stands for P factor, accelerated slipstream, spiraling slipstream, and torque. It's these four invisible forces that all team up to make that left engine failure a real handful. So let's break them down one by one. All right, first up, P for P factor. You might also hear it called asymmetric thrust. So just picture a propeller spinning, right? When the plane is pitched up, like during a climb, the blade that's swinging down takes a much bigger bite of the air than the blade swinging up. And what that does is create this imbalance. You get more thrust on one side of the propeller hub than the other. And here's where it gets interesting. Since both props are spinning clockwise, that P factor actually pushes the center of thrust for both engines over to the right. It's a really subtle shift, but trust me, this is where all the trouble begins. Now take a look at this. You can see exactly why that little shift matters so much. See that distance from the plane's center of gravity to that shifted thrust line? That's called the arm, like a lever. And you can see, clear as day, the right engine has a much longer arm than the left one. So think about it. If the left engine dies, all that power from the right engine is pushing on that super long arm, which forces the plane into a really strong yaw to the left. It's way, way more powerful than the yaw you'd get if the right engine failed. And this right here, this is the big one. P factor is the single biggest reason for all of this. Okay, let's move on to A in our acronym, accelerated slipstream. Now, a prop doesn't just pull the plane forward, right? It's also blasting a high-speed tube of air, the slipstream, back over the wing. And, as you know, faster air over a wing means more lift. And this is where you can really see how these forces start to pile up on each other. Remember how P factor shifted the thrust to the right? Well, that means the most powerful part of that slipstream and all that extra lift it's creating is also on the right side of each engine. So if the left engine fails, you've suddenly got all this extra lift on the right side of the right wing, and you've lost the lift on the left side. The result? A really strong desire for the plane to roll to the left, right into that dead engine.
Next on our list, S for spiraling slipstream. So that air coming off the props, it doesn't just shoot straight back. It actually spirals like a corkscrew. And where that spiraling air hits the plane, well, that makes a huge difference.
Check this out. On a typical twin, the spiraling air from the right engine just kind of flies off into nowhere. But the slipstream from the left engine, it actually hits the tail right on the rudder. That's a good thing. It gives the pilot more control, more rudder authority. But you see where this is going, right? If you lose that left engine, you also lose that helpful little boost of air right when you need it the most, making it even harder to fight that yaw. And that brings us to our final letter, T for torque. And for this one, we have to thank good old Sir Isaac Newton. His third law, for every action there is an equal and opposite reaction, is really the key here.
So as the engines are spinning those props clockwise, to the right, Newton's law says there's an opposite reaction trying to roll the whole plane to the left. Now, think about this. If your right engine fails, the plane wants to roll to the right. But hey, this left rolling torque is actually helping you out. It's fighting that roll. But what if the critical left engine fails? Well, the plane is already trying to roll left, and now the torque from the good engine is just piling on, making that bad situation even worse. Okay, so with all these forces ganging up on the pilot when the left engine fails, you've got to be wondering, isn't there an engineering fix for this? And the answer is yes, absolutely. And it's a pretty brilliant one, too. Let me introduce you to the counter-rotating twin. The idea is simple. Designers made the prop spin in opposite directions, usually inward towards the body of the plane. In this, one little change basically cancels out all those PAST factors we just talked about. The P-factor yawing arms are now perfectly balanced. The torque from the good engine actually helps lift the wing of the dead engine, which is amazing. And now the slipstream from both engines hits the tail, so everything is nice and balanced. It is just a beautiful piece of engineering.
And the result of all this is pretty profound. By making everything symmetrical, the failure of the left engine is no worse than the failure of the right. So on these planes, there is no critical engine. Problem solved. Okay, this is all super interesting theory, I get it. But why does this stuff actually matter to a pilot? Why is it so, well, critical for them to know? It really all boils down to one incredibly important number. And that number is VMC. That stands for minimum controllable airspeed. This is the magic number. It's the absolute slowest you can fly the plane and still be able to control it after that critical engine has failed. If you get any slower than VMC, your rudder just won't be powerful enough to fight against all those yawing and rolling forces. And here is the most important part. Aircraft manufacturers, when they calculate that VMC speed, they base it on the absolute worst-case scenario. I'm talking about losing that critical engine right after takeoff, when you're slow, you're low, and you're heavy. That is the toughest possible situation, and every safety margin, every emergency procedure is built around that one event. So let's wrap this all up. What's the bottom line? On your standard twin-engine plane, the left engine is the critical one. Losing it is more dangerous because of that past cocktail of forces, with P-factor being the biggest troublemaker. But we've also seen how smart engineering, like counter-rotating props, can completely fix the problem. And at the end of the day, knowing this stuff isn't just trivia. It's absolutely essential for pilot training and for keeping the skies safe. So we've kind of pulled back the curtain on the hidden forces that make propeller engines so tricky. But that just leaves us with one more question to chew on, doesn't it? Jet engines. They don't have propellers. So what kind of invisible forces are at play when one of those fails? Well, that's a story for another day. Thanks for joining me.